Okay, Dr. Smith here, still kind of probably a little bit sick. So what I want to talk to you about here, so pardon me if I don't sound great. What I want to talk to you about here is resonance in a tube. And we're talking about sound waves, of course, resonating in a tube. And the tubes you use in this in experiment 9, which is the one we're sort of talking about here, were vertical, but I am going to use a horizontal tube because it makes it a lot easier to plot something if I do a horizontal tube. So what you have is a horizontal tube, and effectively it was closed at one end. I mean, it was really water in the lab that came up into the tube. So this is like your water level here, and this direction, like this was up in the lab. And so effectively you had a tube that was closed at one end, open at the other, and you held a tuning fork at one end to generate sound. And the tuning fork had some frequency f, and the tuning fork would set up a standing wave in the tube. So the question then is, what kind of what's the wavelength of the standing wave in comparison to the length of the tube? So I'm going to call this length L. We found that was the length at which the tube resonated, right? Was L. And so the way the way to think about sound for this lab is sound is a displacement of air molecules. So if there's no sound in this thing, then it just has air molecules scattered all throughout. Okay, no problem, right? Okay, but when you have a sound wave, then at certain points you have the air molecules getting pushed to one side. So you have like the air molecules here getting pushed this way, and so it ends up compressing everything. And then at certain points you have air molecules getting pushed the other way. And so the way I think of this is that, but very very simply, just the wave we're dealing with is movement of air molecules in the direction the wave is traveling. So if you look down here at this end, what happens at this closed end? Can you have air molecules going into the barrier at the end, into the water? In this case, no. You think, in water, sure, there are conditions under which you can sort of cause air bubbles to enter water under high pressure, like carbonation and stuff. But that's at much higher pressures than we're concerned with. Similarly, can you pull the air away from the surface? Well, not really. Again, if you had a massive pressure difference, you could, but you'd need to actually have a vacuum out here in order to create a vacuum down here, which is what you'd get when you move the molecules away. So the answer is no, you can't do either of these things. The air cannot move down there. And so what that means is if we're plotting, say y is our displacement of air, and we plot it going up the tube. Okay, so this is x. X is going in this direction, and then y is the displacement of air we have. We have to have a point here where the displacement is 0. And so, what's the part of a standing wave? What we have is what we're doing. This is just sound going down here, bouncing off this barrier and coming back. And what we saw happen in lab 3 when we did that, was it lab 3? That's right, it was lab 3. When you had a standing wave going, or a wave going this way, and it bounced off a barrier and came back as a wave going this way, the pattern you got was a standing wave. And the standing wave would sort of bounce up this way at one point in time, and then at another point in time it would look that way. But these points in the middle, in between the humps, always stayed stationary. And I should have, hopefully you know this by now. These are the nodes of the standing wave. What this means is if there can't be any displacement here, there must be a node of the standing wave at the surface of the water. Okay, so now if we got a node of the standing wave there, what do we have at this end of the tube? Well, this end of the tube is where the sound is coming out of the tube, right? This is where you're hoping to create a big sound. I mean, you picked a length of this tube. I mean, you moved the tube up and down in the water, but by changing where the water level is, effectively you picked the length of the tube that would resonate at this frequency. And so what you want to have here, actually, you want the resonance, or you want the movement of the air molecules here to be the maximum possible, because this is where your sound that gets outside and goes to your ears is coming from. And so what you want here is, in fact, an antinode. Anti-dash node, there we go, at this position where x equals L. And so maybe it's even clearer if we say the node is at x equals 0 and the antinode is at x equals L. So, what are the possible wavelengths of a wave that would have an antinode at L and a node at 0? Well, let's look at just a standard wave, or a standing wave really, and look at, I don't know, do a standing wave in green. And we'll start like that and go like this, and etc. Okay. And so we're starting here. Here's our node point where we're starting. And we want an L that's long enough that we have an antinode at the end. Well, here are the nodes. I'm going to mark out the nodes in blue. Okay. And the antinodes are here, 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 and so on. Okay, so the first, one obvious possibility is that this could be L. That's getting a little. Is that this could be L? So we could have right there at that point, we could have L equals. How many fractions of a wavelength is this? Well, a wavelength goes all the way from here to here, right? So I think I'm still in bounds drawing here. So this distance here, between this point here, and we go one full wave, this distance here is the wavelength, lambda, right? So this one here is L is 1/4 lambda. Okay, well, what's the next wavelength? Or what's the next possible pipe length that will get us an antinode at one end of the pipe, right here? So I have L equals 3/4 lambda is another possible resonance length. Similarly, L equals 5/4 lambda, and then L equals 7/4 lambda, and so on. So you get the idea here, I hope, that for a single-ended, a tube with one open end and the other one closed, that the possible the resonance frequencies or the resonance lengths are 1/4 lambda, L equals 1/4 lambda, or 3/4 lambda, or 5/4 lambda, etc. So any odd number divided by 4 times the wavelength is a length where you can get resonance. Now, let's look at what happens. Let's move this down a little and say, what happens if you have two open ends to the tube? Well, now what you've got is, remember we said this open end of the tube has to be an antinode, right? Well, guess what? So does this one. Okay, in order to get resonance, you need both ends to be antinodes, which means that if you are looking at, I'm going to do brown for the single open-ended or the double open-ended tube. We're going to start. I'm starting right there. So this goes with this plot. I'm going to start at an antinode, and if we go to the next antinode, then L equals 1/2 lambda. If we go to this antinode, you get L equals, well, actually, L equals lambda. Here you get L equals 3 lambda over 2, and so on and so on. Well, 3/2 lambda, but you get the idea. And so it's easier to see the pattern here. I mean, I think you probably see the pattern if you express this in terms of fourths. So this is 2/4 lambda, this is 4/4 lambda. Sorry, this one here actually is 2/4 lambda. This is 4/4 lambda. This is 6/4 lambda. And so you can see 2/4, 4/4, 6/4, 8/4, etc. are the resonant frequencies for, or sorry, are the resonant lengths for a tube with two open ends. And this is for one open end. So, excuse me, I just probably just smacked my microphone. So if we take, let's see, I'm going to move this out of the way, and then we get, with 2 open ends, we get 2/4 lambda, 4/4 lambda, 6/4 lambda, etc. So these resonant lengths all go in increments of 1/4 of the wavelength. And if you have an odd number of quarter wavelengths, that's a resonant length for a tube with 1 open end, and then I just got email. If you heard that loud noise just now, that was email, sorry. If it's an odd number, then it's for 1 open-end tube, and if it's an even number, it's for 2 open ends. The book covers all this. I think section 17-6, I want to say. Somewhere in section 17 on sound, they actually have a nice diagram in there that I think explains this pretty well. So you can look at this in terms of having one tuning fork and what are the lengths that will work, or you can also look at it in terms of if you have this particular length of tube, what frequencies will work. So let me just okay. So let me just say, you know, if we have, say, a tube of known length, okay, so we have this L, then the first, and let me draw our little XY wave down here. The first resonant frequency is where we have an antinode at y equals 0, and then, or sorry, a node at y equals 0, and then it comes up to an antinode at x equals L. Okay, so this here has a wavelength of 4 times lambda. So this has wavelength equal, I'm sorry, not 4 lambda, 4 L for the blue. Now the next resonant frequency also comes to an antinode, but it goes through, instead of going through just 1/4 of a period, it goes through 3/4. So it goes like this, ends up like that. So this is for lambda equals 4L over 3, because you get through 3/4 of a wavelength here. And then the next one is, you know, we do this in yellow, is 5. So let me see what that's going to look like. That's going to look like that, and then like that, and then something like that. So that's going to be lambda equals 5L over 3, etc., etc. So this one tube can resonate at these frequencies and then at even higher ones. Why did I do 5? No, I'm sorry, that's not 5 lambda over 3. It should be 4 lambda over 5. My mistake. Sorry. So 4 lambda over 5. So you can get the idea then that this tube could then resonate at even higher or even shorter wavelengths, meaning higher frequencies, of course. 4L over 7, 4L over 9, etc., etc. And so one tube can resonate, one tube that's open at one end can resonate at any of these frequencies. And if you have a tube that's open at both ends, like this, length of L, then the possible resonant frequencies are lambda equals really L over, well, let's see. I'm sorry, lambda equals 2L, and then, let's see, wait a minute. Right, and then lambda equals, and then the next one is, I'm trying to think where this, oh boy. So the first one, let's see, the first one looks like this. The next one looks like this. So that must be a wavelength of, that's it, 2/3 L. And then the next one is a wavelength of 2/5 L. Right, and then the wavelength of 2/7 L. So there we go. And so this is for the tube with 2 open ends, and this is the tube with 1 open end. So there you go. That's resonant frequencies.